Hello and welcome to my channel. I'm Sharok, and in this channel I'll be sharing pieces of evolution with you each time. In this episode, we'll be talking about the Big Bang. Please subscribe and don't forget to leave your comments. Thank you. How did our universe come into being? Today, most scientists, astronomers, and cosmologists believe that the universe as we know it emerged from a big explosion that not only created most of the matter in the cosmos, but also established the fundamental laws of physics that govern it. This theory is known as the Big Bang, and for almost a century, many have accepted it as the scientific explanation for the origin of the universe. It stems from the observation that galaxies are rapidly moving away from us in all directions, as if an ancient explosive force is driving them outward. The principles of this theory are relatively simple. In short, the Big Bang hypothesis suggests that all current and past matter in the universe came into existence simultaneously, approximately 13.8 billion years ago. At this moment, all matter was compressed into an incredibly tiny, dense, and unimaginably hot point known as a singularity. It is believed that in such an extremely dense and energetic state, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified as a single force. However, current theories haven't yet managed to explain the mechanics of this single force, as we don't fully understand how gravity functions on subatomic scales. As the universe gradually cooled, became denser, and expanded, quarks and gluons joined together to form protons and neutrons. It took about 180 million years for the first stars to form, and after about 400 million years post-Big Bang, the first galaxies were born. Billions of years after that, stars, galaxies, and cosmic clusters took shape, eventually leading to the formation of the Milky Way and the solar system. The Big Bang occurred 13.8 billion years ago, but it took almost 10 billion years for the solar system to emerge. The Big Bang was just a fraction of a second, but the formation of galaxies has been a process spanning billions of years. According to the Big Bang theory, the universe, as we observe it today, emerged from an initially extremely hot, dense, and almost uniform state. There are four main pieces of evidence supporting this theory. 1. Hubble's law, which shows that the farther away a light source is, the longer its wavelength becomes, indicating the distance between us and that object. 2. The presence of cosmic microwave background radiation, which exists uniformly in all directions, with a temperature just slightly above absolute zero. 3rd, light elements like hydrogen, deuterium, helium-3, helium-4, and lithium-7 that existed in space before the formation of stars. 4. A vast cosmic web that, over time, has become denser and more clustered while the space between its mass increases. These four, Hubble's law, CMB radiation, the abundance of light elements from nucleosynthesis, and the expansion and structure of the universe, form the four cornerstones of the Big Bang theory. In the 1920s, American astronomer Edwin Hubble used the world's largest and most powerful telescope at the time to measure changes in the brightness of various stars over time. This allowed us to calculate the distances to the galaxies in which these stars were located. Hubble's law formula, d is the galaxy's distance, v is its receding velocity, and h0 is the Hubble constant, representing the rate of cosmic expansion, measured as 4 kilometers per second per megaparsec in 2003. According to Hubble's law, the farther a galaxy is from us, the more its light shifts toward longer wavelengths, a phenomenon known as redshift. In the context of general relativity, this redshift indicates a universe in which the fabric of space itself is expanding over time. Consequently, Points in the universe not bound by other forces drift away from each other, and any light emitted shifts toward longer wavelengths as it travels to reach our eyes. Wavelength expansion in cosmic distances and the recession of objects due to universal expansion. There are many explanations for the observed effect in Hubble's law, where galaxies appear to move away from us. But the Big Bang theory offers a unique, simple, and powerful explanation. According to this idea, the universe is expanding, stretching light wavelengths and lowering energy levels and temperatures. This means that as we go back in time, the universe becomes denser and hotter. Over time, as the universe keeps expanding, it gets more crowded, eventually forming larger cosmic structures. If we go far enough back, galaxies are smaller, more numerous, and their stars are younger and bluer. Going even further back, we reach a time when stars hadn't yet had the chance to form. Even further, we find a high-temperature environment in which light separates neutral atoms, creating an ionized plasma that eventually, with cooling, releases the cosmic background radiation. And before all this, the universe was so hot that even atomic nuclei couldn't hold together. As it cooled, the first stable nuclear reactions formed light elements. All these claims were observed and confirmed in the 20th century. However, the Big Bang theory can take us even further back in time, to conditions where energy levels exceed the limits of experimentally tested physics, beyond particle accelerators and cosmic rays. Under such conditions, certain processes must have occurred to create the universe we see today. Something must have generated dark matter. Something must have created more matter than antimatter, and something must have led to the birth of the universe itself. The early Big Bang theory suggested that everything, even space and time, began with this big explosion. But is that really the case? Problems with the Big Bang theory. From the moment the idea of tracing time back to the universe's origin emerged in the 1920s, and again in the 1940s and 1960s, the belief was that the Big Bang would take us all the way to a singular point in time. The original Big Bang concept proposed that if we had a universe filled with matter and energy that had been expanding up to this point, we'd eventually arrive at a point so hot and dense that the laws of physics would cease to function. At this point, density, temperature, and energy reach levels so extreme that the inherent quantum uncertainty, stating we can't simultaneously measure all properties of an electron, leads to logically unsustainable results. In such conditions, quantum fluctuations create black holes that consume the entire universe. Probabilities either turn negative or exceed 1, both of which are impossible in physical reality. We know that gravity and quantum physics don't make sense under these extreme conditions, which is what we call singularity, a point where the laws of physics no longer apply. At this point, it's even possible for space and time to be born. Initially, the Big Bang theory was an idea about the birth of space and time. But all these ideas were based on the assumption that we can trace the Big Bang scenario back as far as we want, to times of infinitely high energy, temperature, and density. Georges Lemaitre, the first to propose the expansion of space-time, said that the Big Bang was a day without a yesterday. But this led to physical mysteries without explanation, such as, why did distant regions of space, which couldn't have had enough time to exchange energy, even if moving at the speed of light, have the same temperature? Why was the initial expansion rate of the universe so perfectly balanced with the total energy amount that it resulted in a flat universe today? And if there were such extremely high temperatures and densities at the beginning, why don't we see any remnants of that era in today's universe? If we only rely on the standard Big Bang theory, the answer is that the universe was simply born this way, with no reason for it. But in physics, that answer feels like giving up. Instead, there's another approach that could explain these observed features while preserving all the successful ideas of the Big Bang. This new approach is known as cosmic inflation. The history of the Big Bang theory. The first clues about the Big Bang emerged from deep space observations in the early 20th century. In 1912, American astronomer Vesto Slipher observed spiral galaxies, then thought to be nebulae, and noticed that nearly all of them were moving away from the Milky Way. In 1922, Russian cosmologist Alexander Friedmann formulated equations, now known as Friedmann's equations, based on Einstein's theory of general relativity. Einstein, then a firm believer in a static universe, relied on a cosmological constant, but Friedmann's calculations suggested the universe was expanding. In 1924, Edwin Hubble measured distances to the nearest spiral nebulae, revealing them as galaxies. At the same time, he developed a series of galactic distance measurement indicators using the 2.5-meter Hooker telescope at Mount Wilson Observatory. In 1929, Hubble discovered a relationship between a galaxy's distance and its receding speed, now known as Hubble's law. In 1927, Georges Lemaitre, a Belgian physicist and Roman Catholic priest, independently derived similar results from Friedmann's equations, concluding that galaxy recession was due to universal expansion. In 1931, he went further, proposing that the universe becomes smaller as we trace back in time, suggesting that at one point, all matter was concentrated at a single point from which space and time originated. These discoveries sparked intense debate among physicists in the 1920s and 1930s, with most scientists favoring the idea of a steady-state universe. This model proposed the continuous creation of new matter as the universe expanded, maintaining a constant uniformity and density of matter over time. Many saw the Big Bang theory as more religious than scientific, perhaps because of Lemaitre's religious background. Other models also gained traction during this period, including Milne's model and the cyclic model, both based on Einstein's general relativity, the latter endorsed by Einstein himself, which proposed that the universe followed endless or undefined cycles. After World War II, the debate between proponents of the steady-state model, led by British astronomer Fred Hoyle, and supporters of the Big Bang theory intensified. Ironically, it was Hoyle who coined the term Big Bang in a BBC radio interview in March 1949, allegedly to critique the theory. If you learned something from this video, make sure to share it with others. Until next time, stay healthy and full of energy. Goodbye.